All right, let's jump straight in. Welcome to the Explainer. Today, we are opening up a seriously fascinating mathematical toolkit. We're taking a comprehensive Arabic mathematics curriculum document, one that's completely focused on the concept of probability, and we're going to translate these seemingly abstract equations into a highly intuitive visual framework. You know, if you've ever felt like probability is just, well, a bunch of random guesses mashed up with confusing Greek letters, you're absolutely in the right place. By the end of this, you're going to see how chance is actually a highly structured, totally measurable, and predictable phenomenon. So let's get to it. Here is our quick roadmap for today. We're hitting the concept and frequency of probability, the basic language of probabilities, rules for calculating events, methods of drawing balls, calculating permutations and combinations, and finally, a real-world application looking at sports. Section 1. Concept and frequency of probability. Before we crunch any numbers, we really need to prove that probability isn't just some made-up theory. Now, take a look at this data-driven proof straight from our source. Imagine actually sitting down and rolling a completely standard normal six-sided die. Not 10 times, but 1,000 times. Sounds tedious, right? But look at the results. The top row shows our possible outcomes, numbers 1 through 6. The bottom row shows how often each number actually popped up. Notice anything weird? Number 1 appeared about 16% of the time, or 0.160. Number 4 appeared exactly 0.166 of the time. Number 6 was 0.174. They are literally all hovering right around the exact same zone. And that brings us to the crucial point here. That stabilization at exactly 0.166, which is just the decimal version of 1/6, is the physical definition of probability. The text highlights that as we increase the number of throws, the frequency of getting a 4, or any specific number, totally stabilizes around this fraction. It's not a guess at all, it's a mathematical certainty that comes from physical repetition. Moving right along to Section 2, Basic Language of Probabilities. Let's map these physical experiments out mathematically. Before we do any calculating, we have to define our universe. This is a foundational term from the curriculum, the sample space. We represent it with the Greek letter omega. The sample space is, simply put, every single possible outcome that could happen in your experiment. Roll a die. Your omega is 1, 2, 3, 4, 5, and 6. Flip a coin. Your omega is just heads and tails. You literally cannot calculate the probability of an event unless you first know the total size of your universe. Okay, Section 3, Rules for Calculating Events. Now that we have our omega universe, let's look at the actual rules. This right here is the absolute golden rule of probability, straight from the text. P of A just means the probability of event A happening. So how do we find it? We take the card, or cardinality, which honestly is just a fancy math term for the simple count of items of event A, and we divide it by the cardinality of omega. In everyday English, the probability of your event is just the number of ways it can happen divided by the total number of possible outcomes. It is really that straightforward, and it's the engine driving this entire toolkit. But what if life gets complicated, and we're tracking multiple events at once? Let's translate this visual notation. Over on the left, that upside-down U shape is called the intersection. Think of it as and. It means event A and event B are happening at the exact same time. It's the overlap. On the right, the normal U shape means union, or. Event A or event B happens. Look closely at that union formula. The probability of A union B equals the probability of A plus the probability of B minus the probability of their intersection. Now, why on earth subtract? Well, because if you just add A and B together, you're actually counting their overlapping middle section twice. The formula perfectly corrects that double count. Which brings us to Section 4, Methods of Drawing Balls. Let's see how this all builds into practice. Picture a classic probability training scenario from our source, drawing colored balls from an opaque box. The curriculum teaches that you have to instantly recognize 3 distinct paths of chance here because the math changes drastically depending on how your hands physically move. First, is a draw simultaneous? Like, are you grabbing 3 balls out at the exact same time? Second, is it successive without replacement? That means pulling one out, holding onto it, and then pulling another. That action completely shrinks your omega for the second draw. Or third, is it successive with replacement? Pulling one, checking its color, and tossing it back in before your next turn. Knowing your physical action dictates the exact formula you need. All right, Section 5, Calculating Permutations and Combinations. Let's look at how we handle massive numbers of possibilities. So think back to our golden rule. We divide our event by omega. But what if omega is absolutely massive? Say you're drawing 4 specific balls out of a box of 100. There's no way you can write all those combinations down, right? The source document tackles this with advanced tools: factorials, that's the exclamation point, combinations, represented by a C, and arrangements, represented by an A. Think of these as mathematical shortcuts. They let us instantly calculate exactly how many ways you can group or order items without having to count them one by one. It's the heavy machinery we bring in when omega gets too big. Finally, Section 6, Application, Sports and Probabilities. Time to put the whole toolkit to the test. Here's an actual, real-world exercise from the curriculum tracking high school students. Group A plays football. Group B plays handball. Group C plays basketball. With a Venn diagram, those intersections and unions we talked about become totally visual. For example, the overlapping sections represent students playing both football and handball, a classic intersection. By applying our formulas, we can calculate the exact probability of picking a random student who plays, let's say, football or basketball. We just add Group A and Group C, and, crucially, remember to subtract those overlapping kids so we don't count them twice. It takes all that abstract math and makes it incredibly practical. To wrap up this explainer, I want to leave you with a thought. We started with the incredibly simple act of rolling a die 1,000 times, and we've ended up with a framework that can actually predict the overlap in complex human behaviors. Probability is absolutely not just a textbook exercise. It's the hidden architecture of chance governing our world. So as you go about your week, try looking at your daily decisions, the traffic route you pick, the grocery line you choose, through this mathematical lens. Ask yourself, what is your omega today? Thanks for exploring this with me.